Okay, a very good day to all of you. Today we are going to learn the Green's theorems in solving the line integral. Okay, let we have the region R be a simply connected plane region whose boundary is a simple, closed, piecewise smooth curve C oriented counterclockwise. Yeah. If fxy and gxy have continuous first partial derivative on some open set containing the region R, then the line integral of, okay, this is a differential form, the line integral of differential form, okay, mxy dx plus n xy dy, in this case line integral on differential form on 2D, where the curve is a closed curve anticlockwise, is equal to the double integral del n del x minus del m del y dA over the region R. So first of all, the curve C must be closed so that it can form a region R, and the curve C must be in the counterclockwise orientation. Then the line integral of 2D differential form on 2D is using Green's theorem. Instead of you evaluate the left hand side here, you can evaluate the double integral del n del x, del n del x minus del m del y dA over the region R. If C is oriented clockwise, the formula becomes it's actually negative of here. So it's del m del y minus del n del x dA over region R. Okay, for example 1, use Green's theorem to evaluate the line integral y cubed dx plus x cubed plus 3xy squared dy along the curve C, where C is a path from 0, 0 to 1, 1 along the graph of y equal to x cubed in the red color, y equal to x cubed, and from 1, 1 to 0, 0 along the graph of y equal to x. Okay, remember in the last lectures on line integral of piecewise smooth curve, if we have line integral on the curve C actually consists of the C1, which is on the curve y equal to x cubed, and from 0, 0 to the point, this point 1, 1, and then from point 1, 1 go back to 0, 0 along the graph C2. C2 is we have y equal to x, C1 is y equal to, this is y equal to x cubed. Hence without using Green's theorem, you need to do the line integral on curve C1 add up with the line integral on curve C2. If you use Green's theorem, since curve C1, C2 in the orientation of anticlockwise and it is simple closed, it forms a region R, then you can evaluate it using the Green's theorem. In Green's theorem, this formula, double integral del n del x minus del m del y dA over the region R. If you're not using Green's theorem, the curve C, you have to break it, becomes C1 and C2. Then you need to evaluate the line integral 2 times. So it's troublesome. If the curve C is anticlockwise and it is a closed curve, then it forms a region R. Then you can evaluate it using Green's theorem. First of all, we look at if we use Green's theorem. So this is the the first one is m. This is the n. The integral of y cubed dx plus x cubed plus 3xy squared dy using Green's theorems will be equal to the double integral, double integral the del x, the coefficient of dy, del x, x cubed plus 3xy squared minus del y, the coefficient for your dx. Okay, so that's your formula in here. M dx plus n dy is del del x coefficient of dy minus del del y the coefficient of the dx. In del del y here. Del del x the n minus del del y the coefficient of dx, which is m here. So it's del del x, x cubed plus 3x y squared minus del del y, y cubed dA. So evaluate partial derivative first. Okay, del del x, x cubed, you have 3x squared. Okay, del del x, okay, 3x y squared, where the 3 is a constant, y squared is constant, that's why I get 3y squared. So minus del del y, y cubed, you got 3y squared, 3y squared, okay. So 3y squared, cancel the 3, minus 3y squared. Okay, the integrand just left integral of 3x squared dA over region R. Okay, the region R, the dA, notice that okay, this is not circular graph, that's why we use Cartesian coordinate to evaluate the double integral, and you notice the region R is formed by okay, the top and bottom curves. So we may solve it using dy dx, where you sum the dA using vertical bar. Okay, so we use dy dx. The lower curve will be a lower limit of your y. Okay, upper curve is the upper limit of y. So mean limit of y from x cubed until x. And you're going to sum the vertical bar, okay, from left, which is x0, until right side, which is x equal to 1. Okay, that's why okay, lower limit is a lower curve, y equal to x cubed, upper limit y equal to x. Sum the vertical bar. Okay, in the region R, from left side, which is x0, until right side, which is x equal to 1. Okay, and then dA, okay, you sum okay, your dA using vertical bar, so it's dy dx. So integrate 3x squared respect to y, okay, where the 3x squared here is a constant, so you have constant multiply y. Okay, so plug in the y from the lower limit x cubed until upper limit x. So you have 3x squared, x minus x cubed, okay, and then you expand, and lastly you integrate respect to x. So mean total this 3x cubed integrate respect to x, so 3x power 4 divided by 4 minus, okay, the second term is total is 3x power 5 minus 3x power 5 integrate respect to x, so minus 3x power 6 divided by 6, plug in your okay, upper limit, okay. Because plug in lower limit, you have 0. The answer is 1/4. Okay, we're going to prove it. Let's say when you haven't learned the Green's theorem, you want to find the line integral of y cubed dx plus x cubed plus 3xy squared dy. Okay, where the curve C from C1, okay, C1 which is y equal to x cubed here. C1 y equal to x cubed, and then okay, from 0, 0 to 1, 1. Later on, from 1, 1, go back to 0, 0 along the curve y equal to x using the parametrics equations. Okay. So first of all, the curve C1 you break into okay, curve C break into C1. C1 is along the curve, okay, y equal to x cubed. Okay, hence you let x here, the right hand side variable x equal to t, then you have y equal to x cubed. Okay, let's the x is t. So y will become t cubed. That's why xt, y is t cubed. Okay, and x from 0 to 1. Right? X move from 0 to 1. So hence t equal to x also move from 0 to 1. So okay, 0 to 1. So x is okay, x is actually t, so t cubed, and then okay, so x is t cubed because along the graph y equal to x cubed. So x is t, y is t cubed. So okay, y is t cubed. Okay, so t cubed. Okay, power 3 again, t power 9. So x is t, so this is t cubed. Okay, and then you have x is t, so dx will be equal to dt. So dx equal to dt. So dy will be 3t squared dt. So plug in x is t, y is t cubed. T cubed, and then you square it, so t power 6. Okay. So you simplify it first. So t power 9 plus t cubed times 3t squared, so 3t power 5. So this is 3t power 7 times 3t power 2. So total is 9t power 9. So and then integrate respect to t. Plug in the limit, you get 3 over 2 along the curve C1. Later on, along the curve C2, where C2 is a curve from 1, 1 to 0, 0 along the graph of y equal to x. Hence, you let x here, you have y equal to x. So let x equal to t, hence y equal to t. X is t, y is t. Okay, x move from 1 to 0. 1 to 0. Okay. Right. X move from 1 to 0, hence t also from 1 to 0. 1 to 0. And then dx will equal to dt, dy equal to dt. So plug in all x, y, dx, dy. Then integrate from 1 to 0. Integrate from 1 to 0. So y cubed will be t cubed, x cubed will be t cubed. So x is t, y is t. So total this will be t power 3. X is t, y is t squared, okay? And y is t squared, and then t squared. So simplify total. So 1t cubed, 2t cubed, and then 3t cubed. Total is 5t cubed. Integrate respect to t. T from 1 to 0. Because x move from 1 to 0, and then this is x equal t. So x also move from, t also move from 1 to 0. So evaluate, you get negative 5 over 4. Hence, the line integral on curve C, which is along the curve C1, which is y equal to x cubed, and along curve C2, which is from y equal to x. Add up the answer. On curve C1, just now we obtained 3 over 2, and curve C2, we obtained negative 5 over 4. So total, which is 1/4, which is tally with the result obtained from Green's theorems. Green's theorem. This is using Green's theorem 1/4. So this example, we purposely show you. Without using Green's theorem, if you want to find the line integral along the curve y equal to x cubed from 0, 0 to 1, 1, and then from 1, 1 to 0, 0, then you need to do your line integral 2 times. 2 times means you do on a line curve C1 using parametric equation where x equal to t, y equal to t cubed, t from 0 to 1. Later on, you do the line integral along the curve C2, where you let x is t, y will be t, x from 1 to 0, hence t from 1 to 0. You add up your answer. You have to do 2 times line integral using parametric equation. Since the curve C1, C2, they are in the anti-clockwise orientation, and it is a closed curve, it forms the region R. Hence, instead of evaluate the line integral 2 times, then you can just use Green's theorem, where you just evaluate your line integral, evaluate the double integral. Instead of evaluate the line integral, you evaluate the double integral. If you have del m integral of m dx plus n dy, then the double integral, using Green's theorem will become double integral del n, del x. Del x coefficient of dy minus the del y coefficient of dx, dA over your region R. If the region R is non-circular, you use Cartesian coordinate. If region R is circular, then you use polar coordinate. And in this case, this region R, I view it as bounded by top and bottom curve. Then I solve it using dy dx. Dy dx means you sum the region R using vertical bar. And then dy dx, you need the limit of y. So the lower curve, y equal to x cubed. This is your lower limit of y equal to x, so x is upper limit of y. and your sums vertical bar from left side, which is x0 until x1. So this is the lower limit of x, upper limit of x. Okay, in the next example, we are directly using Green's theorem. Okay, example 2, use Green's theorem to evaluate the line integral y cubed dx plus x cubed plus 3x y squared dy along curve C, where the C is the boundary of the circle x squared plus y squared equal to 9 oriented counterclockwise. So the curve C here, okay, is a circle with radius 3 units oriented counterclockwise. Okay. If the x squared plus y squared equal to 9 means the R is 3, and the region R is closed. Okay, I mean the curve is closed, it forms a region R, then you can use Green's theorem to evaluate it. And region R is circular, then evaluate a double integral using polar coordinate. Okay, hence this line integral will become, using Green's theorem, will become double integral delta x coefficient of y. Okay, delta x coefficient of y minus delta y coefficient of your dx. Again, the same integral like example 1. So you get 3x squared dA over region R. Region R is circular. Okay, circle with radius 3 units centered at origin. Then dA using polar coordinate, change it become r d theta. X change it become r cos theta. So x squared will be r squared cos squared theta. Okay, r from 0 to 3, theta from 0 to 2 pi, because your region R is a full circle centered at origin. So r 0 to 3, okay, theta 0 to 2 pi. Now it left the problem of double integral using polar coordinate. So 3r squared times r, so total is 3r cubed, where the cos squared theta is constant. So integrate 3r cubed respect to r. We got 3r power 4 divided by 4. Cos squared theta is constant. We just leave it behind first. So evaluate the r from 0 to 3. So here you have the 81. 3 power 4, 81 times 3. So 243 divided by 4. Integrate cos squared theta d theta from 0 to 2 pi. Change the cos squared theta to half. Okay, cos squared theta, you change it to half of 1 plus cos 2 theta. Okay, half of 1 plus cos 2 theta. So half of 1/4, so that's why 243 over 8. Integral of 1 plus cos 2 theta d theta. Then you can integrate it. 1 become theta. Integrate cos 2 theta become positive sin 2 theta divided by 2. Okay, where the theta from 0 to 2 pi. Okay, so plug in theta equal to 2 pi, get 2 pi. Plug in theta equal to 2 pi, sin 4 pi, the answer is 0. Okay, and then plug in theta 0, of course you get 0. Sin 0, you get 0. That's why the answer is 2 pi and 8 here you cancel. So you get 243 pi divided by 4. Okay, this is the second example, where the region R is circular. Okay, without using Green's theorem, we just skip for your own exercise. Okay, example 3, evaluate the line integral arctan x plus y squared dx plus exponent y minus x squared dy, where C is the boundary of the region. Okay, boundary of the region bounded between y equal to the surd 9 minus x squared. Okay, this is a semicircular curve with radius 9 centered at origin, and this is a semicircular curve with radius 1 centered at origin. Okay, oriented counterclockwise as shown here. Okay, C1. If here, C1 is actually y equal to this one. The curve semicircular of 1 minus x squared. when you square it back, this is actually the circle with radius 1. But y equal to positive third means is semicircle, upper semicircle, okay, with radius 1. Okay, C3 is actually y semicircle with radius 3, centered at origin. This is 9 minus x squared. Okay, means if you view it here, along the curve, okay, y equal to C is the boundary of the region bounded between, okay, y equal to third 9 minus x squared and y equal to third 1 minus x squared oriented counterclockwise. Okay, let's see, we view it here. Okay, this curve, the curve y equal to the third 1 minus x squared is C1, because it's, okay, traverse counter anti-clockwise, then move to C2 is here, C2 on the x-axis, C3, okay, C3 in the clockwise direction, anti-clockwise, C1 anti-clockwise, C2, C3 anti-clockwise, C3 along the curve y equal to third 9 minus x squared, okay, until here, until the point x is negative 3, it traverses, okay, along x-axis C4. Okay, that's why, okay, its starting point here, you can see C1, C2 on the x-axis, C3 along the curve y equal to 9 minus, okay, x squared, okay, until x is negative 3, traverse along x-axis again. So it forms, okay, a simple closed curve. Then you have your region R, which is bounded by the curve, okay, y equal to third 1 minus x squared and y equal to third 9 minus x squared. Hence, okay, it forms you have a simple and closed curve which form a region R. Once you can solve your line integral using the Green's theorems. So with the double integral, del del x, the coefficient of dy, del del x coefficient of dy minus del del y, the coefficient of the dx, dA. So del del x exponent y, when the del del x, y is constant. So if del del x constant, you get 0. So del del x negative x squared, you have negative 2x. So minus del del y, when the del del y, okay, x is constant. So del del y constant, you have 0. So del del y positive y squared, you have 2y. So total is negative 2y. Okay, dA. You notice this is circular region. When you square it back, okay, when you square, okay, this curve back is actually you have x squared plus y squared, okay, equal to 9. So means that r equal to 3. Okay, the bigger circle is actually radius, okay, it is a circle with radius r equal to 3. Okay, for the, okay, smaller circle, when you square back the equation, you have x squared plus y squared equal to 1, or r equal to 1. So it's bounded by circular region. Then we solve it using polar coordinate again. So dA become r dr d theta, r, okay, from 1 to 3, because the region is here. This is the region, donut, your donut region. So the r from origin, actually, now if I use other colors, it's, okay, the r actually touch here, the region, okay, touch your region r at r equal to 1 until r equal to 3. So when you rotate, okay, your r actually from here is always touch r equal to 1, r equal to 3, okay, from theta 0 until, okay, then we rotate up to here, okay, you touch this point r1, r3, from theta 0 until theta equal to pi, because it's semicircle. Okay, that's why limit of r is 1 to 3, limit of theta is 0 to pi. Okay, and then, okay, after you, so you factor out negative 2, then you factor out negative 2, this will become, yeah, negative 2, and then integral x plus y dA, x plus y dA. dA you change to r dr d theta, x, okay, Alright, factor out negative 2. X is r cos theta. So factor out r. Y is r sin theta. Now integrate respect to r. So you have r times r, total is r squared. Integrate r squared where the theta is constant. Integrate r squared, r cubed over 3. So become negative 2 divided by 3. Okay. And then, okay, substitute, okay, cos theta, sin theta, maintain that because it's constant. Where the r from 1 to 3. Okay. So you substitute 3 power 3 will be 27. 3 power 3 is 27 minus 1, 26. 26 times 2, which is 52. So negative 52 over 3. Then integrate cos theta plus sin theta d theta. Integrate cos is sin theta. Integrate sin negative cos theta. Plug in theta from 0 to pi. Okay, when you plug in, okay, theta with pi, sin pi you get 0. Sin pi is 0. Cos pi is negative 1. So minus negative 1. Okay, and then sin 0, 0. Cos 0 is negative 1. Cos 0 is 1, but this is minus 1. That's why minus 1. Okay. So total this is 1 plus 1, 2. So 2 times negative 52 over 3. So negative 104 over 3. Okay, so this is okay, the Green's theorem. So I conclude back what we have learned here. To evaluate the line integral of mxy dx plus nxy dy. Okay, line integral of differential form in 2 dimensions only. Yeah? If the curve C is anti-clockwise, okay, you have a simple closed piecewise smooth curve. Okay, like this, like example 1. Okay, you have a curve C1, y equal to x cubed, curve C2, y equal to x. Okay, they traverse in anti-clockwise directions, and the curve is piecewise smooth. C1 is smooth, C2 is smooth. It traverses anti-clockwise and it is closed. Make sure the curve C1, C2, or if you have, let's say, a rectangular region, you have 4 curves. Rectangular region, you have 4 curves. You have a triangular region, you have 3 curves. Make sure all the curves must be traversed anti-clockwise and closed, so that it can form region R. Okay, then instead of you evaluate, for this case, evaluate a line integral 2 times, you just need to evaluate a line integral using Green's theorem. Then you just evaluate your double integral. Mean if the curve C, even though piecewise smooth curve, traverse anti-clockwise, if they are closed, then it forms region R. Then instead of you evaluate a line integral, okay, several times according to how many piecewise smooth curve there, then you just need to evaluate your double integral. Mean you del x coefficient of dy minus you del y coefficient of dx. M is coefficient of dx. Then you del x coefficient of dy minus your del y coefficient of dx. Okay, so this is the integrand of your double integral, and then dA over region R. So the dA can be a Cartesian coordinate if the region R is not circular region. If dA is circular region R is circular region, dA you use polar coordinate, you change it to R dr d theta. Okay, so with this, okay, thank you for watching. Thank you for attention and watching this video.